To start working on functions. These functions are useful, and now we know how to create an array. We'll be able to utilize them and make use out of them and actually start solving some questions. So the functions are going to be in three different categories: some simple manipulations, then how to find specific elements, specifically maximum, minimum, and then we will touch on sorting a little bit. This is the list of table of all the functions, and this is where access is important. Some of these accept access as their argument, as an input, and they have some non-value versions, and none is there's no information, lack of information. None shows lack of information, and if there isn't information, using a simple sum will give us error. So we need to use a non-safe version. Some of them have it, some of them don't, and actually they don't need it. And if they result in an error, we can first check if something is none and replace it with 0. But we are not going to go that deep. Let's just see some examples of these. The function name, if they have an unsafe version, and the description can be found here. And this is just another reminder of access, of each access means and represents. Now let's say we have an array, a 2D array. It starts with 2 square brackets after parentheses. We want to start saying sum and non-sum. So if I go with just the sum, np.sum array, and this is a 2D array, it's going to give me, I haven't specified any access, it's going to give me the summation of all elements. But if I go with sum 0, which is a long access 0, sum access 0, which means go along access 0, along access 0, along rows. So it's going to give me 2 numbers. It is going to go along axis 0, 1, 4, 7, and 2, 5, 8. So I will have two outputs. 4 plus 1 plus 7, it's 5 plus 7 is 12, and the other one, 10, 5, 15. If I go along axis 1, so it's going to be 3 values along axis 1 and 2, 4 and 5, 7 and 8. I'm going along columns, from one column to another column to another column. And I will have 3 values, which is 3, 9, and 15. Now let's say I have a non-value. If I use sum, where I have a non-value in an array, I will get none as a sum, which means literally there was nothing, or all of them are none, and or there is one non-value which I should have not used sum on it without checking. So it's better to use non-safe version, which ignores non-value, and it's going to be 18. Which makes sense, 15 here and 1 and 3 here, which is 18. Just wanted to show the non-safe version and see how it works. And now we know what a long axis 0 means, what a long axis 1 means. Now let's do one more, which is mean and non-mean. Mean gives us the average of the an array. So the average of this array, 2D again, is 35. I can go along axis 0, which means I go row by row. So I will have 3 values, and I can go along axis 1, which means I go column by column, which I will have 2 values for it. Average here is 20, makes sense. 60 divided by 3, and here is 50, which is 150 divided by 3. And then if there is a non-value, I use non-safe version. It's gonna give me 36. If not, it's gonna give me none. It's better to use non-safe versions when we have access to it. Absolute value is just gives me the non-negative portion. If I have an array and I use absolute value on it, np.abs array, it's going to give me absolute value of all the values there. Then the other one that is interesting, and it can be applied to every element. So what's interesting here is we don't need to slice or something. We can slice if we need a summation or average of a portion of a array. But if we don't specify, it's going to go through everything, and it has a like non-slice version of a long sum access. But these are easy to use on arrays. That's why they're important. So we have mean, which one's the minimum value. If we don't specify any access, it's going to give us the minimum of that array, one element, which is here it's 5, a long 0, which means a long rows. I have to go row by row, and it is going to give me 2. And then we have a long column, which is a long column, which is going to give me 3. I'll go column by column. And here, so the minimum here on axis 1, which is a long column, is 10. And here is 5, here is 25, a long rows here. And it is 5 and 15, correct. And again, the difference between non and non-safe. Not non-safe and non-safe. It is the same for maximum. For the same array, we'll get the maximum values. And now you're pretty familiar with axis 0 and axis 1. What does a long mean? And here again, if I go along axis 0, which means I'm going row by row. So I'm gonna only have 2, which is here 25 and 30. And if I go along axis 1, I'm going along columns, column by column, which means I have 3. So now mean and max, np mean and max gives us the minimum and maximum. What if we want to know the index associated with that minimum? We just don't need to know the value. We do need to know the positioning of that value, which test, which row and column is it associated with. We can do that, and argmean gives us the indices to the minimum value. I'm using 1D array intentionally. I'll talk about it later. So it is going to give us the minimum value index. So the mean here is 5, and it sits on index number 1. And if there was a non-value, we better to use non-safe. And here again, it gives us the ignoring none, and it gives us the first index, index number 1. Argmax is the same. It will give us the index for the maximum. I didn't use the 2D for a reason that I'll show a bit further. But let's see where. What does where do, and what is the difference of where and argwhere? So where gives us the values based on a condition. So here, all the values greater than 3, correct? It sits on 3 and 4. Sits on 3 and 4. 0, 1, 2, 3, and 4. All the values greater than 3, the indices associated with them based on a condition. I could have made it, let's make this 20, so you can see the difference. It is first 3 and 4. And then again, it works all the values here greater than 3. Show you this. All the values greater than 3 on 0. 0, 1, 2. So the rows and the columns, correct? Oh, I should have not run on that. So let's go back here. If I need the arrays using where, I can get the indices based on a general condition. Based on a general condition, I can get that. And here, array is greater than 3. I could have gotten for a 2D as well, greater than 3. This gives me the number of rows. I better print something else. So where would give me either rows and columns, and I need to specify the difference. If I asked for the greater than 1, it would have given me a tuple, like let's say array 1, 2, 3, array 1, 0, 2. What it means is the values which are greater than 3, their row values are 1, 2, 2, and their column values are 1, 0, 2. So these are the rows, these are the column. 1, 1, let's see. 1, 1, number 4, correct. 2, 0, 0, 1, 2, and 0, number 2. Sorry, 2, 0, 0, 1, 2, and number 5, it is correct. And 2, 2, which is 6, it is correct. In order to just have access to row, I did slice it. I just said, give me the 0, which is this element in this tuple, and this element in this tuple, which is the first one. I did use a slicing. If I had used this simply, just give me the elements that are greater than 3 in this array called ARR, it would have given me this, which 1, 1, 2, 0, and 2, 2. The indices 0, 0, 1, 1, and 2, 2 were associated in rows and columns. This is what where does. So we know argmin, we know argmax, we know where that will give us a value based on a condition. Nice thing about where, which makes it even a more powerful tool than argwhere, is it can include and consider the exclude ones. So let me go back to the table and show you what I mean. So here I have where can get condition X and Y. What I'm asking here, np where, I'm asking where, let me clear this output. I'm asking where to give me the temperatures more than 25. So if the temperature in temperature array is more than this value, 25 degree, I want this to be considered as hot. So wherever this indices, it is gonna give me a list of column and row and column indices. This is a 1D, so it's just gonna give me one index associated with that column, associated with the vector, and it is gonna go to the feeling hot if that condition exists, if there is a value more than 25. It is gonna read the same index on feeling hot and print that. And if it's not, it's gonna print feeling cool. So this is where the condition is valid. This is where the condition is not valid. And it is gonna print cool, hot, cool, hot, hot. It's reprinted. So 1, 3, 4 are the indices that the condition is met. So 28, 30, and 26. Greater than 25, correct. So it is going to print those for me. If I went 27 and 27 here, you could have seen that there is a change. So that's why Ver is a bit more versatile, because it can accept conditions, print things and go and find and do manipulations way easier for us than the other option, argware. Argware will print the indices in a format of the given array. So, in case you forgot. So argware here, we have 0, 1, 2, 3, 4, 0, 5, 0, 6 was the array. Now I want to print this, oh, I did have it, sorry. In case you forgot, the array ARR is this one. And if I ask it to give me the indices of the values greater than 3, it'll give me 2 and 0, 2 and 2, like, and 1 and 1, instead of giving me 1 row column 1, row 2 column 0. It'll gonna give me a pair of, if it was 3D depth row column, it is 2D, it is gonna give me a row and column. So this is the main difference, the formatting and the fact that where can accept conditions. Now let's go to argmax and argmean that we might use a bit more than conditions. Don't get me wrong, conditions are versatile too, but this is a bit more more basic, I would say. Not in a bad sense, just to understand, and less complex. So here I have an array. I know the argmax, the elements number, but when it is 2D, this is the original array, a 3D array, three square brackets. It's gonna give me 5. What does 5 mean? And what is the maximum value? The maximum value is 29. So what does 5 mean? 1, 2, 3, 4, 5? Like 0, 1, 2, 3, 4, 5. But it is a bit challenging, if specifically if we wanted more information about that location. That's why we use on reveal, and it is going to give us the indices in a shape that we want. So what we do here is we will ask here for the shape of our own original tensor or matrix or array. And it is going to give us, so this has 3 dimensions. It is going to understand based on the shape, the dimension, and then it'll gonna convert number 5 to the position of our maximum value in this case. So let's see if it worked. The value is 29 and it is a 3D index, correct? So first, it is going to be the second layer, number 1 index, 0 for row. So it is in the first row of the second layer, and 1 second column. 1, 0, and again 1, and the value is 29. This is the structure that I suggest to be used to find the maximum or minimum value of vector, matrix, tensor, and any dimension that you have. This will never fail. and you will get the specific information regarding the location of that and index positioning of that value you are looking for, if it's maximum or minimum. And if you have where, like it depends, if you have a condition, it depends on the application and how you are forming your code. Then we have sort. Sort is easy. If you ask to sort, it is going to sort. And then if you want to get the index that will do the sorting for you, you use arcsort. And what I mean is that the result of arcsort is 120, correct? Now, if I use that as a slicing technique, it is going to access those values and put them as first, second, third. So this is going to be the key to the sorting problem. It's going to solve that problem for us, and this is the key for it. And I went a bit fast, I think, but nothing complex. It just needs to be like practiced, and if you do it once, then you know the concept exists and you know how to form your solutions. Here is a simple example that is any engineer's daily work. You have a missed test, you have overheated device, you have a value that is not captured, or it is you know that like somebody had punched the table and it's a vibration test. Any result that would have made that test not reliable or would have gone as none, and then you have your samples in the rows and different observations for the samples. Observations here standing as tests, different tests at each column, and that's how we form our matrix for different samples. And different days might have gone in a 3D and added layers. It depends of the way the test is conducted. But once we form as a 2D, usually samples go on rows and the observations goes on columns, and we might have non-values. So this is a test result of a material which we are interested in finding the breaking point. And we have non-value recorded. And the engineer wants to analyze the data to find the average breaking point, locate the weakest and strongest samples, and then identify which test needs to be reconducted. And then we want to plot, and lack of line means a non-value here. Let's first we need to convert this table to a matrix. We use np array, and they are in megapascal for sure, and np non represent non-values. Then we need to get the average breaking point, and we use non-mean to do so, and mean and maximum values, which will give us the weakest and strongest samples, and that is something that we are interested in. And then we will find the indices using Unravel index approach. And then we have the failed test, which has none inside it. So test 0 and test 1 at, sorry, the first 0 and 1, 0 and 1, 2 and 1. Zero two. Which way? Oh, I use arguer. Arguer, correct. 0 and 2 is the test and the sample that failed. The sample and taste that failed. And 1 and 1 is the sample and test that has failed, and we need to remake that condition and make it again. Our weakest sample has this value, strongest has this value, and this is the location. This is just a print format that you can form. And simple, but insightful information of a table with very simple functions that we just learned. What if we wanted to know like the weakest of each, like the weakest of each sample, the weakest point of each sample? So each sample, we want to, which axis we need to take. This is equal to, we want the each sample collect. We are going to go column by column. So we need first, we need column by column. It is 52.8. Am I going with mean? Yep. So this is the weakest on sample A. On sample B, the weakest is 56.1, and on sample C, it's 54.8. And at each condition, at each test condition, which sample was the weakest, which means going row by row, the zero index. Anyways, so these are like some insightful information that can provide a lot of can increase our understanding of the situation, and we just need some simple functions and methods in Python. Now we want to plot this, and now we know slicing. We can define the samples, we can define tests. It's iron, it's aluminum, it's copper. Test conditions might be different temperatures of something. So we can use, for labels, we can use sample. We are going to plot them in a one figure and using markers, and now that data, now 0, and the other one is going to be everything. So I'm going to have every test on sample 0, which is sample A. And slicing makes our codes neat and still understandable and short. Give label, legend, and show, and this is the style. So here we have failure on test 2, we have failure on test 3 for sample A and sample B, and we can see the trend if there were more tests. Pretty useful. Let's delete these. Now, there is an example of, there are a few examples here under number 1, and you can go through these. Put some hint here, like put your answer here and print your answer, just to practice with the functions. And once you know the functions and you feel comfortable with them, there is a power consumption of electrical device that I have provided, and with some hints. And I didn't provide any hint for plot, just plot here. Plot here, and do not forget to include the library you need for plotting from the previous session. And that's pretty much it. Thanks for paying attention, and see you next time.